Alright, so today we are diving into the wonderful world of radicals. Radical expressions and how to simplify radicals. This is a key concept, just like factoring. You need to know how to simplify radicals. You need to know how to simplify radicals in Algebra 1 and Algebra 2 and beyond. So a radical expression is an expression that contains a radical, obviously. An expression involving a radical with an index and is in simplest form when three conditions are met. Before we talk about those three conditions, take a look and notice the individual components of your radical. You have the radical itself, which is of course this here. The index, which is that small number on the inside right there. Now, when we take the square root of something, we don't often put a 2, it's implied. Just like, remember I have, let's say, the variable a, there's an implied constant 1 in front of that a. So there's an implied 2 unless you specify a different index. And we'll talk about the importance of those indexes or indices here in a minute. The actual number on the inside of your radical is called a radicand. It says an index of 2 is understood but not written in a square root sign, so just like I said. Also, on your calculator, just so you are aware, let's say you want to take something to the fourth root, or to the cubed root. If you're going to take 81 to the fourth root in your calculator, one way to do it, there are a couple different ways. One way is to take 81 to the 1/4 power. If you want to take it cubed, you can take it to the 1/3 power, etc. And if you want to, not cubed, but cube rooted. If you want to take the square root, then of course you can take it to the 1/2 power or just hit your square root button. And then there's also this little button on your calculator that allows you to indicate what type of root you want to input for your index. Okay, so it says simplest form. These conditions have to be met for your radical to be in simplest form. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions. No radicals appear in a denominator of a fraction. So, a couple different things. You want to break down 81 into its product of primes, which we'll do with a factor tree. So we're going to do factor trees a lot in a second. So if you don't like factor trees, you better start liking them. That's what we're going to be doing. So you need to break it down, take out your pairs, and we'll talk about how to do that. And then you've met qualification number 1. 2, you don't want to have any fractions. We'll talk about fractions. 3, no radicals appear in the denominator of the fraction. We'll talk about that tomorrow. Do you have any questions so far? Okay, so how do we simplify radicals? Alright, so we're going to take a look at a property here. First of all, we're going to look at the product property of square roots. The square root of a product equals the product of the square roots of the factors. So, for example, you need to know that when you take the square root of 7 times the square root of 3, you're going to end up with the square root of 21. Or the square root of 9 times the square root of 3, you're going to end up with the square root of 27. Now you can break this down and simplify it, which you will, and that'll end up being 3 square root 3. But just for now, know that when you take the product of two square roots, you would just multiply the radicands and put them under the same radical. You can simplify when possible. So, for example, I know that the square root of 9 is 3, so I went ahead and simplified that to 3. And then the square root of 3 can't be broken down anymore, so I left that the square root of 3. Now, how do we break these things down? That's the question. We're going to take a look at a couple examples of how to break down the radicands so that we are left with prime factors, and we pull out our pairs of prime factors. So we talked about using factor trees. We're going to be using factor trees in order to do this. Okay, so we're going to start with 108. We're going to make a factor tree with 108. Maybe you know 9 and 12 go into it, maybe you don't. If you don't, you can start with 2, it's even. That's 2 and 54. And that's 2 and 27. And what does 27 break down to?
3 and 7. 2, 3 and
3 and 9. And what does 9 break down to?
3 and 3.
3 and 3. So, what I want to do is underneath my radical, I want to write those product of primes. So I have 2 times 2 times 3 times 3 times 3. Now, you're going to pull out pairs. So I like to think of it like prison, okay? So here's prison, and you're trying to escape from your partner, okay? So the rule is you have to escape with a partner, and it has to be the same number. So these two are partners, these two are partners, this whole person doesn't have a partner to escape with, so it stays in prison, yeah? So, partner, one of you escapes, the other one dies. So you're outside of prison. Partner, one of you escapes, the other one dies, and then this whole person is still in prison. At least he's not dead. 2 times 3 is 6. Or just circle the pairs and take one out. Be a little less morbid. Does that make sense? Yeah, 6 root 3, that is the simplified radical. You have a prime factor in here that can't be broken down anymore. And everything that could be broken down, you circle those pairs, you took 1 out. Okay, any questions? Let's look at the next one. So, we already know the square root of 9. What's the square root of 9? 3, so that's easy. Now, we're going to take a look at the variable here. Clear these annotations. So, I already know that the square root of 9 is 3, so I'm going to take that out. Now I have x's. What I want to do is list those x's. X times x times x. Well, you have a pair of x's. You take 1 out. And then 1 by itself. Does that make sense? Now, there are a couple ways you can think about variables. You can either list them all out, which can kind of be a little painstaking, or you can do some division and help you out a little bit so you get a little faster. So what I do is I take the power, and this works for only your variable, okay? So I take that power, and I divide by 2. So I'm taking pairs out, right? So that says I can take 1 pair out, and I have 1 left over. 1 pair is a pair, x and x, right? And then you have 1 left over. If I have x to the 8th, right? I take 8 divided by 2. I could take 4 pairs out, right? You see what I'm doing there? 7. You have x to the 7th. Take 7 divided by 2. How many pairs could you take out? 3 with 1 left over, right? Cool. Does that make sense? Alright. And just to show you visually, x to the 7th, x times x times x, and x times x times x times x. So a pair, a pair, and a pair. So I have 3 pairs I can take out. So that's x times x times x, which is x cubed, right? That's x cubed, and then you have an x left over. That's if I was looking at x to the 7th. If I was square rooting x to the 7th. Does that make sense? Questions? Okay, cool. These are really important. You've seen these before? Yes? These will help you with your factor trees to know these rules. We already know a couple of them, hopefully. Even numbers are divisible by 2, that's really easy. Anything ending in a 0 is divisible by 10, and anything ending in a 0 or 5 is divisible by 5. The rest of these are a little trickier, but I do encourage you to memorize them now because they will serve you very well in the future. And if you think about them, there are little tricks. So 3 and 9 are related. They're also divisible by each other. In order to figure out if something is divisible by 3, the sum of the digits have to be divisible by 3. So for example, 108. Is that divisible by 3? Yeah, because 8 plus 0 plus 1 is 9. That's divisible by 3. For 9, the sum of the digits have to be divisible by 9. Is 8 plus 0 plus 1 divisible by 9? Yeah, so that's divisible by 9. 4 and 8 are related. They just differ slightly. Before, the last 2 digits have to be divisible by 4. So the last 2 digits divisible by 4. 0, 8. Yes, 8, right? Last 3 digits have to be divisible by 8. That one's a little trickier because you have to look at 108 as a whole. And then 6, you have to know the divisibility rules for 2 and 3. And if 2 and 3 work, then it also works for 6. Just helpful hints. Alright, if you're watching the video, I'm not sure if you had time to do this, but here are the answers worked out with the solutions. Well, answers and solutions are the same thing. Here are the questions with the solutions. Oh no. Go back. Alright. Alright, so we have the quotient property of square roots. The square root of a quotient, so we're dividing things, equals the quotient of the square roots of the numerator and denominator. One of our rules said that we cannot have fractions as our radicand, so we're going to have to separate them. So, for example, when I see the square root of 3/4, I have to separate it into the square root of 3 divided by the square root of 4 and then simplify. Always simplify your square roots, just like you want to simplify your fractions, simplify your square roots. So, the first one, square root of 15 over 64. Break that down into what? Yeah, square root of 15 over the square root of 64, and then you see if these will simplify. The first one won't, because it's just 5 and 3, so there's no pairs. So you just leave that alone. The second one will. So that's your answer. Same thing here, square root of 81 over the square root of x squared. Well, these are both perfect squares. What does that give me as an answer? 9 over x. 9 over x. Thank you. Any questions about how to do that? Alright. Notice here it says that you cannot have you have to have a b that's greater than 0. Why? What happens if this is 0? Yeah, can I divide by 0? No. So, it has to be greater than 0. Your top can be 0, because 0 divided by a number is just what? 0. I was going to give you some to practice, but do you feel okay with this? All right. We'll do some of these for bell work. In fact, these will be our bell work tomorrow, so if you want to just take a picture or copy them down, we'll do these for bell work tomorrow. But I will project those. All right. I'll give you your simplifying radicals worksheet, and then we're going to go on